In the event the United States lost its overseas Air Force bases, our Air Force would be at a definite strategic disadvantage if another war took place. The present-day problem of how to locate, identify, and destroy strategic enemy targets would be greatly intensified. The loss of these bases is a possibility that could become a reality within the next 10 years due to the ever-changing political scene. Faced with this problem, the Air Force, after 1965, must have an advanced strategic weapon system that has global flight capabilities. Such a system must be accurate, reliable, invulnerable, versatile, and must have a designed-in growth potential. The strategic weapon systems presently under development do not meet all these requirements. Intercontinental ballistic missiles will be of tremendous value by 1965. However, by their very nature, they cannot obtain the necessary reconnaissance data, pinpoint bombing accuracy, or indirect bomb damage assessment. In fact, the effective use of intercontinental missiles may well depend on reconnaissance information obtained by an advanced weapon system. To fill this need, Bell Aircraft has been working since 1951 on a bomber reconnaissance weapon system. Research and development was started as a company-sponsored effort with the Air Force supporting the project since 1954. We call it Bomi, a contraction of bomber missile. It combines the best features of manned strategic aircraft and long-range missiles. Basically, it is a manned hypersonic rocket-powered glider that meets requirements for either bombing or reconnaissance missions over a global range. The heart of the system is a manned airplane which will be propelled by 3 rocket boosters to a final altitude of approximately 300,000 feet and a velocity of 18,000 miles per hour. Elapsed flight time around the globe from takeoff to landing will be slightly over 2 hours. While possessing global flight capabilities, its size will be much smaller than the modern B-52 strategic bomber. A comparison of weight and size is shown on this chart. It is 25 feet shorter in length than the B-52. Bomi's gross weight is even less at takeoff, and its empty weight is much less than the present-day bomber. Previously, I mentioned the 5 basic criteria that such a weapon system must incorporate. The first is accuracy. The future targets will not be large cities and industrial complexes, but selective and heavily defended targets such as underground factories and hangars, airfields, runways, and launch sites. This will be objectives of future strategic Bomi attacks. The great accuracy required is assured by Bomi's navigation and bombing systems. The type system employed makes it unnecessary to know the exact target location prior to takeoff. By the combination of missile type guidance and human intelligence, the Bomi system will identify and destroy targets by direct observation or by using terrain checkpoints. The inertial system, supplemented by the crew and their optional radar or optical monitoring equipment, gives Bomi a 1,500-foot circular error of probability. Using nuclear warheads, this CEP will result in the destruction of all types of targets. Reliability is the next military advantage of Bomi. By adding the crew to the system, human judgment can be exercised and corrective action taken if necessary. In addition to its monetary function, The crew will constitute a complete auxiliary control and guidance system, a fact that further gives Bomi the capability of fulfilling its mission, even though system malfunctions might be experienced. Due to the short flight time, pilot fatigue will not exist. This fact also increases the reliability of the system. High altitudes and hypersonic speeds are the most significant factors contributing to the invulnerability of Bomi. When considered in terms of exposure to enemy defense, these factors make it a very desirable weapon system. Once Bomi is into its horizontal flight path, lateral decoy maneuvers can be employed to make it impossible for the enemy to predict exactly where it will go and where its guided bomb will strike. The detection range for Bomi will be much shorter than for an ICBM weapon system. In addition, the enemy will have all the interception problems associated with an ICBM and more, since they will not be able to forecast Bomi's flight course or destination. Another military advantage of Bomi is its versatility. It will be capable of flying more than one type of strategic mission. With a simple designed-in capsule arrangement, reconnaissance equipment can be substituted for the bomb. This versatility greatly reduces the need for more than one type aircraft to perform various strategic missions. This fact alone would contribute greatly to the economy of conducting strategic operations. Any future weapon system concept, such as Bomi, must have a designed-in growth potential to assure a long operational life. As more efficient power plants and propellants are developed, system performance will be improved without major design changes. Since Bomi will be traveling at velocities close to those of a satellite, the system could also be utilized as a vehicle for space research. Bomi has a growth potential as well as other capabilities for meeting the strict requirements of an advanced strategic weapons system. Now let's see what a typical Bomi operation might look like in 1965. Since the support equipment is mobile and permanent installations are not required, launching sites can be easily established. The platform will be of simple construction, consisting of an open flame-diverting pit and a horizontal assembly rack which raises Bomi to a vertical launch position. The second stage booster is positioned horizontally on the assembly rack. This is followed by the first stage boosters, which are then attached on each side to the second stage booster. The airplane, after being armed with a warhead, is positioned in tandem to the second stage booster. While the system is still in its horizontal position, the various subsystems are checked out and preliminary system functional checks are performed. After completion of assembly and checkout, Bomi is raised to a vertical position over the flame diverting pit. The final systems check then takes place and the fueling operation starts, followed by activation of the coolant system. When the fueling operation is completed, the crew enters their sealed, conditioned cabin and gives the autopilot a final check. After the mission profile is set into the inertial navigation system, Bomi is ready to be launched and the area is cleared by ground personnel.
Pressurized lock tanks, pressurized fuel tanks, tank valves open, start pumps, lock bleeds open, lock bleeds closed, actuate igniters,
Igniter's okay.
start engines,
Engine's okay.
Actuate main stage.
Main stage okay. Ship away.
During takeoff, Bomi is controlled by gimbal-mounted engines during its programmed turn. When it reaches a climbing angle of 40 degrees, an approximate altitude of 60,000 feet, and a velocity of 4,000 miles per hour, the first stage propellant supply burns out, and the first stage boosters are separated. At a climbing angle of 4 degrees, an approximate altitude of 200,000 feet, and a velocity of 12,000 miles per hour, the second stage engine fuel supply is exhausted, and the second stage booster is then separated. And the third stage rockets in the airplanes are ignited. Throughout the entire ascent and acceleration, the flight house has been carefully controlled by the navigation and stabilization systems. Crew function has been limited to checking the various systems against malfunctions. When the airplane propellants are expanded, Bomi will be traveling in a normal flight attitude at an approximate altitude of 300,000 feet and at a speed of 18,000 miles per hour. The airplane now begins its glide flight, during which its tremendous kinetic energy will be expended, giving it great range covering ability. The glide is a gradual but constant descent in altitude and reduction in velocity. During the extremely high altitude and high speed phase of the mission, the available aerodynamic forces are small, but fortunately the control forces required are relatively small also. Control is maintained through the use of small reaction jets located near the control surfaces. The jets are actuated simultaneously with these surfaces. As the airplane glides to lower altitudes and denser atmosphere, adequate control can be maintained by the aerodynamic surfaces alone. Because of Bomi's high speeds during the glide phase, it is expected that temperatures up to 2,000 degrees Fahrenheit will be reached at various portions of the airplane. To overcome this problem, Bell Aircraft used the double wall design principle and water cooling of the primary structure. The water is expended in the form of steam continuously from the time Bomi reaches its maximum velocity. At the leading edges, where the airplane reaches temperatures beyond material strength limits, liquid metal cooling has been provided. 95% of the outer skin is separated from the cooled inner wall by a layer of light insulating material. With this protection, most of the heat incurred from air friction is radiated outward from the airplane. The double wall construction and water cooling system not only maintains structural integrity, but also prevents heat from entering the equipment and crew areas. The crew compartment is completely sealed, and the environmental atmosphere is provided from stored gases carried aboard the aircraft. Compartment temperature is controlled by the water system used to cool the structure. By these means, the conditions within the compartment will be maintained at very comfortable values throughout the flight. The pilot and navigator will be seated in a normal position. The acceleration forces during the entire flight will at no time be more than those experienced by present-day fighter pilots. Since the start of the glide phase, the navigator has been comparing Bomi's flight path by radar returns against previously obtained displays of the areas over which the air flying. These displays are continuous presentations driven by the inertial system and are compared against the radar returns being received. Particular geographical features such as lakes, river junctions and cities are especially checked. The flight paths may be corrected as required from this comparison. Errors in the navigation system and in our knowledge of geographical location of targets can be corrected in this way. The pilot, during this phase of flight, monitors the various systems, the plane's attitude, speed, and altitude, and takes corrective action if necessary. As the aircraft approaches the target area, the inertial system computes the range to go and compares this with the range at which the bomb is scheduled to be launched. When these ranges coincide, the bomb will be launched automatically. The controllable bomb, unpowered, is directed essentially in a ballistic trajectory towards the estimated coordinate target location. Due to the fact that the bomb is launched about 300 miles from the target and that the airplane passes over the target area about 1 minute before the bomb strikes, the crew has time to observe checkpoints around the target and transmit any necessary corrections to the bomb. With a CEP of 1,500 feet and the use of nuclear bombs, coupled with the crew's ability to take corrective actions, the destruction of any target is assured. At detonation, the airplane is 100 miles beyond the target area and can record data such as altitude, direction, time of drop, and elapsed time to detonation. The information is obtained through optical and electronic equipment, thus affording adequate indirect bomb damage assessment. Its target destroyed, Bomi continues on its glide flight to a predetermined landing site. It will continue to decrease its altitude and velocity until it reaches approximately 100,000 feet and 4,000 miles per hour above the landing point. A beacon system may be provided to aid the pilot in locating the landing field from the high altitude at which the descent is made. He can then take over from the inertial navigation system. Through the use of other landing aids, such as Bell Aircraft's automatic landing system, coupled with standard approach control systems, complete automatic landings can be provided, assuring all weather operations. After a total flight time of slightly over 2 hours, Bomi touches down at its home base at an approximate speed of 140 miles per hour. Its mission successfully completed. You have just seen a bombing mission that Bomi will be capable of performing in about 1965. The mere knowledge of Bomi's existence and capabilities will act as a deterrent of war. The development of this weapon system is a necessity. In 10 years, the present concept of intercontinental strategic operations will be a thing of the past. We must develop an advanced manned strategic weapon system that has global capabilities and will be invulnerable to any foreseeable defense.